So we are going to be starting out with some mechanisms and predicting the product for an electrophilic aromatic substitution reaction. So whenever you have a primary alkyl halide and you're doing a Friedel-Crafts alkylation reaction, you need to think about rearrangement. Because if it's larger, if the primary group is larger than an ethyl group, then a rearrangement will occur. So let's look at how that would work. So we can redraw the alkyl chloride and the Lewis acid, and then we're going to show a nucleophilic attack. The Lewis acid base reaction that forms the complex that essentially activates the alkyl halide to make it a better electrophile. We draw our Lewis acid base complex, and then in this case we combine loss of a leaving group with a hydride or a methyl shift in this case, because we don't want to draw any primary carbocation. So if I just drew this arrow, I would have to draw a primary carbocation. So that's not good. So instead of that, I'm going to do a simultaneous hydride shift to generate a much more stable intermediate. So once I have done that, or sorry, I keep saying hydride shift, but of course what I'm doing is a methyl shift. So once I have done the methyl shift, I end up with a tertiary carbocation and the byproduct, aluminum base leaving group. So from here, we can do our aromatic ring involved. And we have an isopropyl group already on the ring. So this is going to be an ortho-para director, and it will direct para first. And it would only go ortho if the para position was blocked. In this case, it is not. So in order to show the para position attacking, we want to utilize whatever pi bond is associated with that position. That's going to give us this intermediate, which we need to do a final proton transfer to get the aromatic product. So you can draw out the aluminum tetrachloride, or you can just use a chloride that will have formed from dissociation with the Lewis acid. This can be used as the base to regenerate the aromatic ring. And this gives us the product, which I'll go ahead and draw up here by the reaction. And just to kind of fit it, I'm just going to shift the ring around a little bit. It's easier to fit on the paper. And byproduct of that last step, which is seal. Okay, let's look at the next one. This one is a Friedel-Crafts acylation reaction, because we're looking at an acyl halide. So, first step is generating the active electrophile. We take our acyl halide and react it with the Lewis acid. One of the lone pairs on the chlorines does a nucleophilic attack, generating a complex. Which now has a great leaving group. Because it has a great leaving group, it's optional to draw the additional arrow on and the oxygen. Go ahead and draw that. This is the more stable resonance contributor, so that's why I opted to go ahead and generate that one. And a byproduct of this step will be the leading. Now that we have the acylium ion, which is the active electrophile in this reaction, we can go ahead and get the aromatic ring involved. Again, we are dealing with isopropylbenzene, so still an ortho para director, directing primarily para. I'm going to have that pi bond attached to the para position. Tank. So that introduces the acyl group in that para position. And the final proton transfer again to generate the aromatic product. This generates our product, which actually I might draw from here just because there's more room. Right. So moving on, we're going to be doing a little bit of review, identifying the compounds as aromatic, anti-aromatic, or non-aromatic. Remember, with me as instructor, you're typically going to get some wording such as assuming adjacent p orbitals are coplanar. That's an assumption you need to make because otherwise you could have a p orbital all the way around the ring, but the ring could deviate from planarity through bending. Essentially, it's flat shape into some other non-flat shape, in which case it would be difficult to predict if it's going to be anti-aromatic or non-aromatic or aromatic because we don't know exactly what the shape of the molecules are. And if they deviate from planarity, that is difficult to predict. So to make it easier, I actually introduced this term so that if we know there's a p orbital everywhere, then we assign it as, we assume it's going to be planar. And that will actually help with doing some of these assignments. Okay, so when we're looking at this one, remember that there's 3 pi bonds. It kind of looks like benzene, and it's very similar to benzene. And because there's already there's the 3 pi bonds, all of the p orbitals are coming from the pi bonds, which means these lone pairs don't count towards aromaticity. Those 3 lone pairs are all in sp2 hybridized orbitals, where the p orbital on each nitrogen is part of the pi bond. So it does meet the first criteria in that there is a p orbital all the way around the ring. And if we count up the electrons in those p orbitals, there's 2 electrons for each pi bond. That's 6 electrons. That is an aromatic number of electrons, so this is aromatic. You can think of it as 6 electrons or 3 electron pairs, an odd number of electron pairs, aromatic number. Okay, if we're looking at this one, you need to think about the p orbital situation. There's clearly a p orbital at each of those carbons for the pi bond. When you have a carbocation, there's an empty p orbital there. There is a p orbital, doesn't have any electrons, but there's a p orbital. And then in order for this to potentially be aromatic, that means there has to be a p orbital at each of these oxygens, which would mean one of these lone pairs would have to be in that p orbital. basically, if I'm going to call it potentially aromatic or anti-aromatic, I need a p orbital all the way around the ring. So that would mean that the oxygens would have to have a p orbital. So it's potential p orbital, also potentially a hybridized orbital, depending on if we can call it aromatic or not. So let's look it up. So if we say, okay, let's assume for now that the lone pairs are in p orbitals. That would make a p orbital all the way around. Then we count up the electron pairs. We have 1 electron pair, 2 electron pairs, and 3 electron pairs, and then this one is empty. That's actually an odd number of electron pairs. That would make this aromatic. So having those lone pairs in p orbitals is advantageous because now the molecule can have aromatic stability. There's actually a resonance contributor you could draw for this one. It might look something like this. Which might be a little bit easier for you to see that it's aromatic, because you would have the 2 electrons in each pi bond, 4 electrons, and then one of the lone pairs in the p orbital. Count. Making 6 pi electrons. Okay, so these are. All right, let's look at the next one. So the next one, we have kind of a similar situation with the oxygen atoms. So we have p orbitals everywhere where there's pi bond. And then in order for this to potentially be aromatic, you would have to have a p orbital at both oxygens, which would mean one of these lone pairs on each oxygen would need to go into it. The problem with that is when we count up the electrons, now we would have 1, 2, 3, 4, 5, 6, 7, 8, or an even number of electron pairs. So that's not good. This would make this anti-aromatic. The thing with heteroatoms with a lone pair, or lone pairs in general, is they can choose to go into p orbital or a hybridized orbital, and where they will go is whatever makes the molecule stable. So in this particular case, if we place these lone pairs in a p orbital, that would make it unstable. So they won't go into a p orbital. They will go into sp2. Sorry, sp3 hybridized orbital. And that would mean that there is no p orbital at those oxygens, which would mean it cannot be aromatic or anti-aromatic. Instead, it's going to be non-aromatic. So let's sort of compare the 2 cases here, right, where we did different things with the lone pairs. And here we put the lone pairs in the p orbitals. Here we put the lone pairs in sp3 hybridized orbitals. And that's because when I put both of these lone pairs into a p orbital, such that I had a p orbital all the way around the ring, then I counted up the electrons, and it was an aromatic number of electrons in the p orbitals. That makes it stable, so that will happen. Over here, if I put these 2 lone pairs in a p orbital, it would have an anti-aromatic number of electrons, which would make it unstable. Instead, it will go into a hybridized orbital, an sp3 hybridized to be specific, and that means there's no p orbital here, and it doesn't match either criteria for aromatic or anti-aromatic. Okay. Moving on, this is the tryptolium ion. I have a 7-membered ring with 3 lone pairs and a positive charge. It is aromatic because there's a p orbital all the way around the ring. And there's an empty p orbital on the carbocation. And there is 3 electron pairs, which is an odd number of electron pairs. Okay, moving on to this one. This is where we would potentially come up with a different answer depending on whether or not we were making this assumption. So I'm making the assumption that if there's a p orbital all the way around the ring, that it's coplanar. In this case, there is every single carbon atom all the way around the ring has a pi bond. So there's a p orbital everywhere around it. If we assume that means that it's coplanar, right, then we can count up all the electrons. 1, 2, 3, 4, 5, 7, 8, 9, 10 electron pairs. Right? So 10 is an even number of electron pairs. Okay, so that means that right? So of course, in reality, it will deviate from planarity. So, and especially because there's some steric interactions with the hydrogens here. Right? So it will deviate from being a totally planar molecule, which will mean that the p orbitals don't overlap, which would make it non-aromatic. Okay, so most cases in a situation like this, it doesn't have to be planar, and if planar means that it's anti-aromatic, we'll adopt a different conformation. Okay, but if we assume that they're all coplanar, right, and that there's no problem with them all being coplanar, and we just have to count up the electron pairs and see if we have an even or an odd number of electrons. So we have 10, which is an even number. Okay, so, and again, on the key, I think they're not making this assumption. So it's assumed then that it would deviate from planarity and become non-aromatic. Okay, hopefully that makes sense. Let's move on to this one. Right, so everywhere you see a pi bond, there will be a p orbital. And then there's an oxygen atom with 2 lone pairs. So this is a situation where we have to think about whether or not one of those lone pairs might exist in a p orbital. Okay? If it does exist in a p orbital, that would make 1, 2, 3 electron pairs, which is a aromatic number of electrons. So that means it will go into a p orbital. And we will have aromatic. We're looking at the next one, right? This one almost looks like the tryptophan ion, but there's no ion here. This carbon is actually sp3, which means there's no p orbital there. There's no p orbital, it cannot be aromatic or anti-aromatic. Okay, so for the next one, look at where the p orbitals would be. So we have p, p, and then in order for this to have a p orbital all the way around the ring, that would mean that both lone pairs need to exist in a p orbital. If we do that, we have the wrong number of electrons. We have 1, 2, 3, 4, 5, 6, 7, 8. That's 8. That's anti-aromatic. Okay, so it's not going to go into a p orbital if it would make the molecule anti-aromatic. As a result, these will go into hybridized sp3, hybridized orbitals, and you'll have non-aromatic. Moving on to the next question. Select all compounds Okay, so actually I have some horrible shadowing. Okay, so all compounds that will not undergo a Friedel-Crafts reaction, either acylation or alkylation. So remember that we cannot do a Friedel-Crafts alkylation or acylation on a ring that is either moderately or strongly deactivated. So if it has a moderate and strong deactivator on it and nothing to counterbalance that, it will not be able to undergo a Friedel-Crafts reaction. The reason for that is that the electrophile is not a strong enough electrophile to overcome the strongly deactivated and very, very weak electrophile reaction. So you might recognize right away that a nitro group is a strong deactivator. So this one will not be able to undergo a Friedel-Crafts reaction. And then in addition to that, a nitrogen with a positive charge directly attached to the rings also is strong deactivator. So these cannot undergo Friedel-Crafts reactions. So these all, when you have a nitrogen that doesn't have a positive charge, it isn't a nitro group, then it's a strong activator and it will definitely be able to. And then in this case, we have both a moderate activator and a weak deactivator. So either way, it's not moderately or strongly deactivated. Overall, it's fine. Let's look at the next question, which talks about the fact that dimethylaniline is able to undergo a electrophilic aromatic bromination. And you get, as expected, a mixture of ortho and para products because the dimethyl group is a strong activator and ortho para director. But that same group that's typically a strong activator and ortho para director somehow doesn't direct the incoming nitro group into a para or ortho position. Instead, it goes to a meta position. So the explanation for that is actually looking at the reagent. This is nitric acid. It's a strong acid. So strong acids will react with amines to act as a base and protonate the amine. Right? There was no strong acid. But amines are basic, right? The lone pair there is basic. So it can pick up a proton from a strong acid. And as a result, now it is a strong deactivator. So it converts what used to be a strong activator into a strong deactivator. The deactivators are meta-directors. So that explains the introduction of the nitro group in the meta position. So the protonated group is a strong deactivator. And again, it's the acid-base reaction that can occur here. Okay. Moving on, we're going to fill in some boxes, the appropriate product. So the first case, we are doing a bromination benzene, and it doesn't really matter where you put that bromine. It's benzene, so all the positions are. And then it says magnesium, and then acetone. So magnesium will generate a Grignard reagent, and after attacking acetone, will create a new carbon-carbon bond. And I'm also assuming that there's an acidic workup to provide that proton. Okay, so just in case you don't know, acetone, two methyl groups. Okay, Next one is starting out with a Friedel-Crafts alkylation reaction. Now we'll introduce a methyl group. That methyl group is a orthopara director, activator, and orthopara director. So it will direct the. This one is a little bit tricky because in some conditions the nitro group might go ortho. But then usually orthopara directors direct both. So I'm actually wants you to learn about this, but I guess I'll just pick what I would prefer. So we're just going to basically assume that all orthopara directors direct para first. And so the methyl group will direct the incoming nitro group. Again, there are conditions with which you might get more ortho product in this one particular reaction, which is an exception to the rule. So, but with that, we're just going to say orthopara directors direct para first, only direct ortho when para is blocked. So now we can do excess NBS, and that is going to brominate the benzylic position in this case 3 times because there's 3 hydrogens here. So we want to convert that to a CPR3. And the next one, the bromination going on, and it's going para to the strongest activator, oxygen. So that makes sense. In order to do bromine, we use Br2 and some sort of acid. Sometimes it's just written as iron, or aluminum tribromide, or iron tribromide. So it's completely optional. Different Lewis acids can be used here. So that will again introduce that bromine in this position. That's where the activating group is directing. And then it looks like we need to make a carbon-carbon bond. Carbon-carbon bond here needs to be made. So we're going to introduce an electrophile with 1, 2, 3, 4 carbons. And whenever your oxygen ends up 1 further carbon away from what you would expect from a carbonyl. So for example, this is the new carbon bond here. So this means that the OH group is at carbon number 1 with respect to the new carbon-carbon bond. Whereas over here, it's at carbon 2. So this tells me that I need to use an epoxide and not an aldehyde or ketone. So for that, I'm going to use magnesium to generate the Grignard reagent, the alkyl bromide. And then I'm going to introduce epoxide. Just have 4 carbons. And we assume an acidic. So now we're practicing synthesis. We're going to synthesize the following targets starting from benzene. And then just pay careful attention to the fact that we cannot do any sort of Friedel-Crafts reaction on a moderately or strongly deactivated system. Okay, so looking at this one, I probably don't want to introduce the nitro first, because if I do, it is a meta director. I might be able to get this group on, but there would be a very difficult time getting this ortho nitro. So it makes more sense probably to introduce an ortho para director here and eventually convert that to a. So if I start with benzene, I can do a Friedel-Crafts alkylation. Introduce a methyl group. Now that is an ortho para director. So if I do it again, the next one will go para to the original methyl. So from here, now I have two ortho para directors where para is blocked, which means that the ortho positions are activated, and they're all equivalent because of the two planes of symmetry. So it doesn't really matter where you put it, the same equivalent position. So now we're going to do the nitration conditions, which is nitric acid and sulfuric acid. That will introduce the nitric. Now I can convert my methyl groups into the carboxylic acid. And I can do this through oxidation. So potassium permanganate or sodium dichromate. And I need multiple equivalents because I've oxidized two benzoic positions. So we use excess. And this will get me to okay. Next one, we have this meta substitution. So if I introduce the chlorine first, that's an ortho para director. So that means any incoming group would go here. That's not good. But I can remember that I can get an amino group from a nitro group. And nitro group meta directors. So if we introduce a nitro group first, we start with benzene, nitration. That's introducing nitro group, which is now a meta director. Remember, I can't do a Friedel-Crafts reaction on this, but I can still introduce a chlorine. No problem. That is not a Friedel-Crafts reaction. Again, the nitro group directs meta. I'm going to be directing a chlorine to the position that I want it. Now I just need to reduce the nitro group to the next one has 4 groups. There's a lot going on. But one of the things I can look at it and say, okay, this is an alkyl group, so it'll be ortho para directing. This nitro group will be meta directing. If I'm able to get these two on, these two will be nicely directed into the correct positions. This is ortho to the alkyl group and meta to the nitro group. So in order to get the nitro group and the tert-butyl group on there, I need to put the tert-butyl group on first. So you can Friedel-Crafts alkylation reaction, which would introduce the tert-butyl group, which is now a para director. Now I can introduce the nitro group. Now, both of those groups are directing to these two positions. So just sequentially add a chlorine and a bromine, and it doesn't really matter in which order. First. So the bromination second, and a little tight to draw that in. So it's the right product. So for the next one, we have these 3 groups, and they're all meta to each other. So we definitely want to avoid any ortho para directors because we'll have a problem directing to the right position. So I definitely don't want to put in the chlorine first. So instead, I might introduce either the nitro or the acyl group first. You have to be careful because if I introduce the nitro group first, I won't be able to introduce the acyl group second. Just remember, we cannot do a Friedel-Crafts reaction on a moderately or powerfully deactivated ring. So I actually have to sequence this correctly, in that I need to introduce the acyl group first. If I tried to do the nitro group first, it would not work. Introduce the acyl group first. Now this is a meta director, so it will introduce the incoming nitro group to the meta position on the ring. Our nitro group will be properly directed where we want it to go. And now we have two meta directors. So we're doubly directing to this position, which is great. And right now we would not be able to do a Friedel-Crafts reaction on this powerfully deactivated ring, but we can introduce it. The next one, we have an isopropyl group, a halogen, a nitro, and an acyl group. So it kind of reminds me of the previous one, but with this added isopropyl group. So one of the things that I think about when I look at something like this is the fact that this isopropyl group is an orthopara director. And all these groups are orthopara to it. So it might be nice to use that as a directing group, introduce all those other groups. So if we wanted to do that, we could start by introducing the isopropyl group. Friedel-Crafts alkylation. I'm going to put it here. Everything's just going to rotate. And then after that, right, this is definitely going to direct para. I'm going to introduce acyl group. So I don't confuse you with the fact that I've kind of rotated the ring. So from here, the acyl group is directing meta, and the isopropyl group is directing ortho. So they're directing to the same position. So at this point, we can either introduce the nitro or the halogen. And I would introduce the nitro first, just because the nitro will help direct the chlorine into the meta position. Whereas the chlorine is an orthopara director. That could be problematic. So my preference is to do nitration first. I think it'll be cleaner overall to do it this way. So now the isopropyl group is directing here, nitro and the acyl group are directing. So super directed, and we'll be able to introduce the chlorine in the last step. Product. Okay, last one on this page. Starting from benzene, we have to kind of make this fairly complicated. So the problem with potentially doing an alkylation, introduce this ring, is that it was going to be a primary alkyl halide, and those can be arranged. So it's actually best to do a double acylation. And it's has more steps this way. It happens once and then it happens the other side. It's more steps because then now I have to reduce those two. And that zinc mercury amalgam but it proceeds with no rearrangement, which is really helpful. Now I've reduced, really you're going to need excess because you're going to reduce both. Now we have that second ring, which is a ortho-para director because it's an alkyl group. Those are weak activators and ortho-para directors. These two positions are equivalent because of the plane of symmetry. And in this case, I am going to choose, I need to introduce the sulfonyl group and the chlorine. I think it makes more sense to introduce the chlorine first. And that's because as soon as we introduce the chlorine here, this is now an ortho-para director as well. The para is blocked. So that means that it's going to introduce the sulfonyl group ortho to help direct. Whereas if I introduce the sulfonyl group first, then the sulfonyl group is a meta-director. So it would be trying to direct it to another position. Now it wouldn't be the strongest activator, right? The strongest activator decides, so it would still produce the product, but it would be in contrast, right? Whereas if we introduce the chlorine first, everything's directing to the same position, there's no contrast. So I just think it's a better. So to introduce the sulfonyl group, we need the fuming or concentrated H2SO4. So the next question is a mechanism. And we're starting from anisole, and we are doing that reaction that we actually just utilized in the synthesis problem, that double Crafts acylation reaction. So we can show that by starting with acyl halide. And remember, if you're drawing a mechanism, please draw in all the lone pairs. So it's going to react with the Lewis acid on the complex. This is just like any other Friedel-Crafts acylation that you might have done. The mechanism. Don't get overwhelmed by the fact that there's two acyl halides. That's okay. We'll deal with them one at a time. Once that chlorine is activated to the leaving group, it can leave. To form the active electrophile, in this case, which is the acylium ion. And then as soon as the acylium ion is generated, we can put our aromatic ring involved. We're starting with anisole. And anisole, the oxygen here is a sort of on the borderline between the moderate and powerful activator. Either way, it's an ortho-para director. So it will direct para first. Use that pi bond specifically. Now we can draw the aromatic ring. After it's done its nucleophilic attack, carbocation here, introduced the acyl group, and we have the 2-methylene and other. We always show proton transfer to regenerate the aromatic ring. You can just draw in some chloride to use for that proton transfer. So that will regenerate aromaticity and stability. Drawing all those lone pairs seems tedious, but that's actually helpful to follows. We have a byproduct of HCl. Okay, so we're almost there. Right? We've introduced this new carbon-carbon bond in the product, right? But we need to introduce it again over here. We need to make both of those. So we again need to activate the second acyl halide to form an oxonium ion that can be attacked by the ring. So the same sort of steps will take place. We're going to form a new complex, second acyl halide. Once we have our complex, use that as a leading group, form a acylium ion, which we know can be attacked by the ring. Draw that acylium ion. Try to make sure we don't add any or lose any carbons on accident. Right, and now it's going to come over here. We can use this carbon. And you see the new one is formed. It's going to form a 6-membered ring, which is a stable ring size. We're almost out of space, but we need it. Charge here, proton here, which needs to be removed. Final proton transfer chloride to regenerate the aromatic ring. Get to the product, we generated the second one of HCl as byproduct. So there's the entire thing. Last question here. We need another mechanism. We want to figure out what form is that giving it to us in this case. Let's see if we can figure it out. So first of all, we're treating this structure with magnesium. So we're going to be forming a green. We can just go ahead and draw in that green reagent. We don't draw the mechanism for the formation of the green reagent anyway. So we'll just go ahead and say, okay. Here, we have magnesium associated with carbon halogen. So we know now that this carbon is strongly basic, right? So it can attack electrophilic carbonyl carbons like an ester. In this case, a cyclic ester. We need to move electrons up to the oxygen. This is going to be kind of fun to draw here. We have this 5-membered ring that we have not yet broken. We've got the alkoxide when you're attacking. And then we have 2-carbon bridge between the two. They're going to be the 2 bridges. So we can kind of go up here, 1, 2, attack. Count the number of carbons consistent with what we had before. Okay, so from here, now we can have loss of a leaving group. We can figure it out. So when we do that, we end up with a 6 carbonyl, kicked out leaving group, which ends up with an alkoxide, and then the acidic workup will provide the proton. make the product. So we leave product here. Provides the proton. So we just want to make sure then that it matches the molecular weight. So you can do kind of a quick calculation there. So we have 6 carbons. This is a 6-member ring. So 6 times 12 plus, which is 72, if I can do math today, which is a challenge. And so I have 2 oxygens. So 2 oxygen weighs 2 hydrogens. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have done this math right. So likely to be